Hello and welcome. We will be examining pairwise sequence alignment, specifically how to take two protein sequences and optimally align them. Pairwise sequence alignment is a fundamental application of bioinformatics that other programs and algorithms build upon. Objectives for this session include defining orthologs and paralogs. These are both terms that refer to types of homology. Homologous sequences are sequences that share a common ancestor. We will align globin proteins using the two most commonly used algorithms for pairwise alignment. Those are BLAST and L-align, and then analyze that output. The output can be different depending on the algorithm. We will look at two different types or strategies for alignment, the global and the local. And finally, run the global and local algorithms for comparison's sake. We will be using 4 protein sequences in this session. 3 are human proteins, and 1 is a mouse protein. I've also included the identifiers. So human hemoglobin subunit alpha, if you want to retrieve that sequence from the NCBI sequence database, its identifier is 4504345. I've included the other identifiers for the other sequences. The second is mouse hemoglobin subunit alpha. It is called an ortholog. It's the equivalent or most related protein to the human hemoglobin subunit alpha. Orthologs tend to be closely related sequences, but across species. The final 2 sequences are also relatives of hemoglobin subunit alpha. Subunit beta shares a common ancestor through gene duplication. Human myoglobin also shares a common ancestor with subunit alpha. Now, within species, when there are sequences that are related, those are called paralogs. So the first 2 sequences are orthologous. Those are orthologs, the mouse hemoglobin alpha and the human hemoglobin alpha. But the other 3 human proteins, all of which are related, are considered paralogs. Those are homologs or relatives within the same species. We're going to look to see what the most closely related sequences of this bunch are, and you may be surprised by the answer. Okay, so let's jump right in. The 2 most commonly used programs are BLAST and L-align. I will start with BLAST. That is found at NCBI. Just type in BLAST and then the NCBI address. Okay, you see a BLAST menu, which I will get to shortly. I'm going to pull up the actual sequences here. Here are the sequences. Remember, they are in FASTA format, which, as we've learned, include a descriptive title and the actual amino acid sequence in 1-letter code. So this would be the sequence for human subunit alpha. Mus musculus is mouse, so here is the mouse hemoglobin subunit alpha sequence. And finally, here is subunit beta and human myoglobin. Okay, so we are going to want to align subunit alpha from human and subunit alpha from mouse. This will be our first exercise. So on the BLAST menu, you'll see 5 different types of BLAST. Nucleotide BLAST is for DNA sequences. We have protein sequences, so we're going to use protein BLAST. I should point out that the other 3 are translated BLAST, which are a little more complex, and that will be for another lesson. So click Protein BLAST, and notice that there is only one window to enter a sequence, because this is set for database search mode, and that would be to allow users to do a BLAST search. We're not doing that yet. We are just going to compare 2 sequences, and you'll notice that there is a checkbox by what I just highlighted. Align 2 or more sequences just below the job title. If I click that box, the second window opens up. Now I can paste in my sequences. So here is subunit alpha from human. I'll paste that into the top window. Finally, subunit alpha from mouse, I'm going to paste that into the bottom window. And you see that BLAST-P is the algorithm that is set, so I'm just going to hit BLAST. The results come up pretty quickly since I'm only comparing 2 sequences. And you see some parameters, a score of 255. I'll explain a little bit more about that. And here's the actual alignment. The top sequence is the human sequence, so here are amino acids 1 through 60 of the human, and then 61 through 120. Finally, the rest of it is here. On the third line is the mouse sequence. And in the middle, you see a series of letters, some spaces, and some plus signs. I'll explain what that means. When you see a string of letters, that means that they are identical at that position. So NVLS and NVLS are identical in human and mouse. And where you see the space, okay, the PA does not match the GE, so there's no capital letter in the middle. Capital letter indicates an exact match. And finally, the plus sign is for amino acids that are chemically close. So there is V and I. That's valine and isoleucine, so they count a little bit. So here we have identities and positives, and I'll explain shortly what that means. But what we can say is that the proteins are 87% identical and 92% similar. Very, very closely related proteins. You'll notice that there are no gaps in the alignment. It goes straight through. These proteins are the same size, so these proteins were very, very easy to align. Very identical in size, and they matched up very well. Let's remember that. 87% identical and 92% positive. So what exactly does that mean? Let's look at the similarities, but first let's start with identity. Identity is the extent to which two sequences are invariant, meaning the amino acids have to be an exact match. So in that alignment, 87% of the positions had an exact match. However, similarity includes the exact matches and what are called close matches. We also call those conserved matches. Now note that some amino acids are chemically very similar. For instance, isoleucine and valine, and arginine and lysine. Arginine and lysine are the two positively charged amino acids, so they're very similar in chemistry. So we count those in addition to the exact matches when we measure similarity. The alignment we just saw was 87% identical and 92% similar. What that means is that 87% of the positions were exact matches, and an additional 5% included close matches or conserved positions. So we say that these proteins are 87% identical and 92% similar, so very, very close. Okay, let's compare two different proteins, but this time we're going to use the L-align program. L-align was developed by William Pearson at the University of Virginia, and you can see that the L-align site allows for two windows as well. So what we are going to do this time is compare human subunit alpha and human subunit beta. Subunit alpha in the first window and beta in the second window. It's a different algorithm, but it's pretty similar. I'm going to hit align sequences. First of all, you notice that the output is a little bit different, using double dot for identical and a single dot for similar. So the Q and the K here are similar, and here is a stretch of VK and VK. That matches exactly. Also notice that there are gaps in the sequence, meaning that these proteins were not exactly the same size. We see 43.4% identity and 74.5% similarity. That's lower than what we saw with the human and mouse proteins. So we really can conclude that the human subunit alpha and the mouse subunit alpha are closer relatives than the two human proteins of subunit alpha and subunit beta. It may surprise you, and this might be a good topic for discussion, that the human and mouse proteins' common ancestor was more recent than a common ancestor between subunit alpha and subunit beta. We notice there are gaps in the sequence because it's a little more difficult to align, and what it comes down to with pairwise alignment is optimally placing the gaps. That's really the nature of the problem with pairwise alignment. In any alignment, there really are only three possibilities at every position. That could be an exact match, that could be a mismatch, or there could be a gap. Matches and mismatches are scored using a substitution matrix. Remember, some amino acids are chemically similar, so some mismatches are better than some other mismatches. A mismatch that maintains similar chemistry will score higher than a mismatch that completely changes the chemistry of the protein. And finally, a gap. And with a gap, there tends to be a penalty for the existence of a gap and a penalty for the length of the gap. Okay, so here's a substitution matrix, and this basically is a scoring mechanism for every single amino acid pair. So when a C is paired with a C, it scores 9 points. When a C is paired with an E, that's very different in chemistry, that scores a -4. But some mismatches actually get a positive score. For instance, S and A. You look in the second column, and then you go down to the A row, which is the 5th row, that scores a +1. It's a fairly complex scoring system, and the idea behind the algorithm is to show the alignment that has the best score. One of the first successful strategies with developing pairwise alignment was by Needleman-Wunsch in 1970. It's called global alignment. The idea is to align the proteins completely from the start to the finish. It works very, very well for close relatives and for proteins that are the same size, exactly the same length. In 1881, Smith and Waterman developed what's called local alignment, and local alignment doesn't necessarily require the sequences be the same size. It tends to be better for most sequences. I included a web link that was placed up to compare local and global alignment, and if you want to follow it, you might find it helpful. Okay, so let's try to compare some global and local strategies at the European Bioinformatics Institute, or EBI. There is a pairwise alignment suite, and it's at the EBI address, www.ebi.ac.uk/tools/PSA. Once we're there, we're going to select the Needle program for global. Needle stands for Needleman-Wunsch. And we'll select the Water program for local. Smith-Waterman for local. Okay, so here's the pairwise alignment suite. We can scroll down a little bit and see the Needle program in BOSS. And then here's the Water program using the Smith-Waterman algorithm. Open the protein version of the Needleman-Wunsch. Here it is. So again, we got 2 sequence windows. Let's try subunit alpha. And this time a more distant relative, which is myoglobin. So I've got subunit alpha from human, and I've got myoglobin from human. So now submit, and we see an alignment. We see some lines, some dots, and some double dots. I'll explain that shortly. We see 26.5% identity and 40% similarity. Let me also try the same with local alignment. So I'm going to open the Water program. Alpha in the top window. Myoglobin in the bottom window.
Hold on. I gotta find out where that noise is coming from. I think it's over here.
And the similarity scores are pretty similar. 41.6% similar. Note that the Needleman-Wunsch program has a gap in the top sequence, a gap in the bottom sequence. And you'll also notice that myoglobin has all 154 amino acids shown, and hemoglobin is a shorter sequence. Subunit alpha is only 142 amino acids. Notice here that it didn't even show the last 6 amino acids on the local alignment program. It only aligned the regions that were supposed to align. And typically, what the difference is between global and local alignment is that global tries to align across the entire length of the sequence, even though the lengths are different. Where local, it's not so concerned if there's a sequence that's a little bit longer or there's a longer end to a particular protein. It won't even try to align that part. And notice also there's a gap here, a short gap here. Similar results. So with these particular proteins, we got somewhat similar results with both algorithms. However, with some proteins that are more distantly related to the ones we just saw, you would see that local alignment tends to work a little bit better than global for most proteins. In general, local was an improvement of the pairwise alignment process that came about 10 years after the development of the global program. Also notice that there are vertical lines, dots, and double dots. There are 3 categories. And remember, we only have identities and similarities. So let me explain what the notation means. Okay, first notice that all of the vertical lines represent exact matches. So you see the LLL at the beginning, and then the A to A, and the V to V. Well, there are 2 levels of similarity. For somewhat similar to get 1 dot, and for very similar, you get 2 dots. That's really the only difference in this output versus what we saw with BLAST and L-align. Just note that different algorithms show different outputs, and be aware of that when you do pairwise alignment. That concludes this lesson. Please feel free to jump in using these sequences or finding your own to align. You do want to use proteins that are related. This process is designed for related proteins. Good luck.